Yesterday was version 1.0. Today is 2.0 in transformation. Okay? Real quick reminder. Somebody help me out here. What were the three transformations we talked about? What was one of them? Very good. Reflection. Who's got one of the other? Rotation. Translation. When you see reflection, what's the trigger word that goes with it? Flip it. What about rotation? Turn it. What about translation? Slide it. All right, not that bad. Okay, y'all got me? What? It's okay, you can say it. Okay, flip one, turn one, slide one. Right? What you got to figure out. Make that hard. Okay. Now, I said it was transformations 2.0. That's what I mean by that. We're going to put everything in a coordinate plane, okay, and we're going to move it around today. Flipping them and redrawing them and all sorts of stuff. Okay, it's going to be real fun. Isn't it, Miss Bowen? Pardon me, Miss Bowen. It's going to be fun today, right? Yeah, we're going to have fun today. All right, so check it out, y'all. Reflections. Anytime a point is reflected, we have what is called the line of reflection. That line of reflection forms a perpendicular bisector with each particular point that we are reflecting across. And it's also congruent. What's congruent? Same from line of reflection to each particular point. So in this example, if point A gets reflected to the other side of this line of reflection, it is equidistant and it forms a 90-degree angle. Once we put this onto a graph, an XY coordinate plane, a Cartesian plane, check it out, we got three of them. If I flipped or if I reflected across the x-axis from P to P prime, my x values do not change. My y values go from positive to negative or negative to positive. Okay? And instead of saying positive, negative, negative, positive, I say the opposite. We have y, and we have the opposite of y, which is negative y. Or we have negative y, we have the opposite of negative y, which is positive y. Positive, negative, negative, positive. Okay? All right. I could also reflect across the y-axis, go from P to P prime. Notice what happens. My y values stay the same. My x values, I take the opposite of the x value that I'm getting. Pretty simple, right? So far, got harder. If you don't hate me yet, you'll hate me soon, okay? Because it's going to get real tough. If I reflect across the line y equals x, I got to take my x and y, my original x, y points, and switch them. So check this out. I gave this some coordinate points here. Let's go with 2, 1, 2, 3, 4. 2, 4, right? That's where P is. 2, 4 is where P is. But P prime is at 1, 2, 3, 4, 1, 2. See how I've got to switch my x and y's when I do my prime reflection? Right, that's some of the stuff we're going to be working on today. Any questions on that? Sweet. If I wanted to get out stuff, we can draw all this out. That's how we do it. Step 1, through each vertex, draw a line perpendicular to the line of reflection. Vertex. There's a good vocab word from last week you're going to see on Mars quiz. Mars quiz. Mars quiz, right? Okay. What is a vertex? No. We can throw other vocab words out there. Parallel. I had that earlier. Two lines together, and what do they form? A vertex. Thank you. when a line segment or a ray intersects with another line segment or ray, they form an angle. And the point that angle is created is called the vertex. Okay? So if you want to get real technical with it, the angle is everything represented in red. The vertex is the black dot. Okay? Get real technical. So when it says draw a line through each vertex, it means from the point that the angle is created. But you don't want to get technical with it? Well, we're not going to get jiggy with it, so we're just going to be very technical. Okay? All right, then, check it out. I form perpendicular lines with each particular vertex. Measure the distance from each vertex to the line of reflection. Locate the image on each vertex to the opposite side of the line of reflection and say this is from it. Okay, it's the way of saying equidistant. If I were going to draw a perfect triangle reflected across that white line, I would take 1, 2. We'll take that point. 1, 2, 3, 4. We'll take that point. We'll take this point. We'll call this 2 units. We'll call this 4 units, and we'll call this 2 units. And what we would do is, we would, of course, have ourselves a good-looking triangle here, right? And on the opposite side of my line of reflection, I would go down 2 units, go down 4 units, go down 2 units, and I would have my next triangle, which, of course, as I'm drawing it, is perfectly reflected. Outstanding job, Mr. Hobbs. Thank you. Okay. No, it's not a perfect reflection. There's some sarcasm. But you get the idea, right? That's the equidistant. Okay? All right. The crux of our material today is going to deal with things like this. Okay? We also talked about translation. Woo-hoo! One of my favorites. Translation. Okay? It's a transformation along a vector, right? Such that each segment joining a point and its image has the same length as the vector and is parallel to the vector. Key word you need to remember, parallel. Okay? Parallel. Translation has to be parallel. Not too bad. Horizontal translations along a vector. If I move horizontally, all I change is my x value, right or left. If my x value that I'm translating is negative, I go left. If it's positive, I go to the right. For a vertical translation, I'm moving it up or down. If my y value is positive, I go up. If it's negative, I go down. Notice something. Did my x values ever change? No, I never moved along the x-axis. Here, did my y values ever change? No, Sensei, I never moved along the y-axis. Then I get to the general translations along the vector, right? And then all of a sudden, I got to move things left, right, and up and down. So let's see how we do with this. If I start at this point, point P, let's call point P -1, 1. There's -1, 1. And I add this transformation and move point P, let's go. Make it easy. I move point P 2 units to the right, 1, 2, and 1, 2, 3 units, 2 units up. If I make a 2-2 transformation, I go from this point right here, I move 2 units to the right, 1, 2, 2 units up, 1, 2. And I've got my particular change. Okay. You don't see this today and tomorrow. We don't on this today. Trying to go with it 2 hours. Okay. Here is an example of some of the instructions you get. Needless to say, we might be doing this. Okay. You do not have to worry about this particular drawing of a transformation. I would be very surprised if our great state of Georgia puts this on the EOC in the same manner. As a matter of fact, I've checked with the engineers at Georgia Tech, and you can actually use a computer if you ever have to do this in real life. So we're just gonna kind of show it up here and say, there it is. There's some stuff involved with it. Okay. If you want to know how it is, though, the big thing is keeping the lines what? Parallel. Okay. Whenever you have translation and you're moving several different lines, it's called line of transformation has to be parallel. Right. Last one is my favorite. All right. A rotation. When I say rotation, what do you think? What do you think? Yeah, like turning, man. Yeah, that's it. Turn it. Turn it. Now check it out, y'all. On a test or a quiz, I would tell you to turn things clockwise or counterclockwise. In class, if I don't specify it, always turn it counterclockwise. Cool enough? I don't specify it in class, turn it counterclockwise. Right? Our center of rotation, point P, the images, pardon me, the points have to be equidistant from that center of rotation. And here's the kicker. All angles from vertex P, with a vertex of P formed by a point and its image are congruent. What's congruent mean? Equal or the same. Doesn't mean similar. No, does not mean similar. All right? Actually, it will be similar later. It doesn't always be similar. Technically speaking, everything that's congruent is similar, but not everything that's similar is congruent. See where we're going in this class? Voodoo land. All right, here we go. Rotating things 90 degrees counterclockwise about the origin. I'll make this easy for you. 1, 2, 3, 4, up, 1, 2. Point P is at point 4, 2. If I rotate point P 90 degrees counterclockwise about the origin, I can take these simple tasks. My P prime, see how this says negative yx? Go back to your original coordinates. Take the opposite. I know, it's time. Take the opposite of y. Use that as the new x coordinate. Take the original x coordinate and use it as your y coordinate. Sounds simple enough. It'll be hard once you get in there. Negative 1, 2, 1, 2, 3, 4 is how I would do that problem. Okay? We're going to be working on coordinate plane, obey. These are the keys. These are like the tools that you're going to use to get through today's classwork. Okay? And they will be on your classwork. So I see none of you are taking notes. Some people are. So you got them in your head, right? Okay. All right. What about 180 degree rotation? Okay. 180 degree rotation, I simply have to take the opposite xy that I started there. All right. Oh, that ain't that bad, is it? Let's do a little quick little 4-minute assessment. Let's say that's point P. Okay. Let's say I have this point. 1, 2, 3, negative 3, 2. That is point T. Negative 3, 2. What would a 180 degree rotation of that look like? One guy got it right. Take the opposite of 3, which is what? I'm sorry, the opposite of negative 3, which is what? Positive 3. What's the opposite of positive 2? Where is the point? 3, negative 2. 1, 2, 3. Down 2. There is, okay, there is my T prime. That's 180 degree rotation. Doesn't matter if I go counterclockwise or clockwise. What? Does it matter if I go Counterclockwise or clockwise? No, it doesn't matter. It's the same spot either way, right? That's the whole point of being 180 degrees. Got me? Check it out. Watch this. Cameron. I'm going to do a 180 degree rotation counterclockwise and look at you. You ready? Go. Got me? See where I'm standing now? Right now. I'm going to do a 180 degree rotation clockwise and look at you. Did it matter? No, it didn't matter at all. Okay? Got it? One day you'll look here. It's okay. It's okay. You can go either way with it. Just follow the rules, right? And here is an example of how I would, well, how you can draw this out if you need to freehand, right? All of the examples about how to draw it are things that you can do freehand. You don't have to have a coordinate plane, which I hate, because I'm always going to give you a coordinate plane to try to do these. Don't you agree? Good. I can draw a segment from each vertex to point Q. Let's try this whole vertex thing again. What's a vertex? The point of the angle. Very good. Construct an angle can grow to A on each segment. Measure this between each vertex and point Q. Mark out this as our corresponding grade to locate the image of each vertex. Right? That's what they're doing right here, okay? They're taking each particular vertex and marking off that point. Each of these angles is congruent to angle A. That's right. And then they're going to connect each particular vertex together. I'm never going to get there. And not just y'all, I'm just saying in this class. To me, this isn't even something that, this is cool geometry stuff that maybe we should do more of. Maybe we'll come back to it in April when everybody's really bored, okay? So we'll see. All right? You won't be really bored, I promise. Any questions on any of this?